Hello friends, welcome to this video, and in this video we are going to implement the attention unit architecture in the PyTorch framework. So let's get started. So our first question is, what is attention unit? So it is an image segmentation architecture that combines the popular unit architecture with an attention mechanism, or we can say the attention gate, which is a proposed term used in the paper. In one line, we can say attention unit is equals to unit plus attention gate. Now let's have a look at the block diagram of the attention unit given in the proposed paper. So this is the block diagram, and if you see, this attention unit is designed for 3D segmentation, but we'll implement it for 2D segmentation. So we'll begin with input image. So here if you see input image, it shows 1 by height, by width and depth. So 1 here refers to number of channels. So if you see this is the format according to PyTorch. Okay, in PyTorch we first have number of channels, then height, then width, and then depth. So because we are working on 2D segmentation, just ignore these D's in this entire block diagram. So just we're going to deal with channels, height and width. So we began with this first input, that is the input image. After that we have this triangle, and if you see here, this triangle represent a convolution operation with ReLU activation function, and it is repeated 2 times. After that it has two things. First is this skip connection, which goes to the attention block, attention gate, which goes into the decoder block, and the output here this layer passes via the max pool layer, which decreases its height and width by a factor of 2, and like this we follow. So this part indicates the encoder block. In between we have this cone block. I usually call this as cone block or convolution block because there is just convolution and ReLU layer. So here if you observe, they have just used convolution layer and the ReLU activation function. No batch normalization is there. But the standard nowadays is that you use convolution in normalization layer and then activation function. So what I'll do, I'll add the batch normalization in between the cone and the ReLU layer. But if you want, you can follow the original implementation, that is convolution then followed by ReLU activation function. Okay, this is all about this encoder and the mid part. Now we come to the decoder. If you see this circle with the curved line, it indicates the attention gate, their proposed novelty in this paper. So this attention mechanism, if you say, is basically a simple TTL attention. If you say, it take the previous output from previous block, okay, and then the skip connection. So I have just studied this paper and seen its block diagram, which I'll show you in the later slide. So what I feel is that this attention gate is simply improving your skip connection feature map. So in UNET, what we do, we simply concatenate them. So here what they have just done, they have added this attention gate in between. So what this do is it improve the feature maps. Now let's go on to the decoder part. So here if you see, first we have a concatenation with this is with the output of attention gate. Okay, then it is followed by this convolution block, and like this we goes on, and at the end we have our segmentation. So this is all about the description or the about the attention block. So let's move on to the next part. So next we have an encoder block. So for easiness, I have divided this entire architecture into blocks. So what we're gonna do, we're gonna first learn about a block and then implement it in the PyTorch framework. So encoder block is used to extract high level input feature from the input image. Second, this input block consists of a series of cone 2D layer, batch normalization and ReLU layer. So now we go on to the block diagram. So first we have the input. Okay, so if this is the first encoder block, your input would be the input image, and if it is second or third encoder block, then it would be the output of previous block. So we first have this cone 2D layer, then batch normalization, and then a ReLU activation function. Again, we have same set of layer repeating. Now, here the output of ReLU act as skip connection, and this output of ReLU also passes via the max pool, and it acts as the input for the next block. So now we have studied about this encoder block. So what we'll do, we'll move on to our text editor and start with the implementation. So first of all, we are going to import the torch library. So if you are new to the PyTorch, then just don't worry. It's really simple like TensorFlow. I say it's much more easy and better than TensorFlow in some cases. Like for research paper, I usually use PyTorch now. I feel really easy, and it's easily customizable. It has more customizability, what I personally feel. So like in TensorFlow, we used to import layers from like TensorFlow.keras.layer size. So here we just import these two points, and I think we are done for most of the time. You can have some other things required, but not now here. So in TensorFlow or Keras, we usually build function, which I do. Here we build class. Okay, we basically build a subclass of NN.module. So let's see. So here we'll build a conv class conv block. So inside it, we're gonna say NN.module. So if you have studied the concept of OOP, oops, basically what I meant. So this is a subclass of this parent class. Okay, so this NN.module is the parent class, and this conv block is a subclass or child class. Next, we're going to define the INIT, that is the constructor. I hope you all are like getting things, understanding my points, what I'm trying to convey here. So see, if you have any issue, then please write that issue in the comment box below. I'll try to answer them. Okay, so let's move. Now here we need to write this statement. See, even I don't know what this does, but what I have from my like capability or my analysis is that because we are using this this inheritance concept, so we need to write it somehow. It is related to this base class or the main class. Just ignore it. Like these things are like repeating in every. So inside this initializer, we take two inputs, inc and the outc. So inc basically mean input channels, outc means out channel. So here in PyTorch, we need to specify both the input number of channel and the output number of channel. While in TensorFlow, this part comes easier in TensorFlow. There you need to just specify the number of output channel and you're done. Okay, but it's easy. So let's now create some of our layer. So we're going to say self.conv. So here we're going to use nn.sequential. Next, we need to define our layers here. Let's go back to our slide. So if you see, we have first conv layer, base normalization, and ReLU, and then we are repeating same set of layer. Okay, first what we're going to do, nn.conv 2d. So inside it, first we're gonna give the number of input channel, number of output channel, then the kernel size, then padding. So in TensorFlow we say padding same, but here we need to manually specify it, how many padding. Okay, next base normalization. Okay, it should be capital. Okay, next ReLU activation function should be capital. Okay, so we've defined these layer. Now what I'm going to do, I'm going to copy paste them, because we are repeating same set of layer just with one slight difference. So if you see, the number of output channel are out underscore c. So the number of input channel for conv 2d layer, this specific layer, would be out c. Okay, now this is the initializer part. Here we define the layers. Now we have a function called forward. Self x as the input. Self.conv, we're going to call the set of layers and give it the input x. So this is your conv block. Now next, in the same way, we're going to define the encoder block. So now what I'll do, I'll simply copy this part, because I know this part is repeating except the name. We need to change this name. Encoder block. Okay, rest everything is same. Now again here we're going to define our layers. Conv. So here we can call this conv block class. Give it its parameter or arguments. Next we're going to define the pooling layer. So we're going to call it pool. It's a 2 by 2 pooling. Now we need to go to forward self, then x. Now we're going to say s, that is output of conv, that of convolution layer. Input would be x. Now p, output of pooling layer. We're going to say self dot pool. Your input would be s. So s represent the skip connection and p represent the output of pooling. So skip connection will go to the attention block, then decoder part, and p would go to the next encoder block. So we're going to give these two things back, s comma p. So this is our encoder block. So now what we'll do, we'll implement the attention unit. So we're going to say class attention unit nn dot module. Okay, again initializer. This time we don't need any input for this attention unit. Then super underscore init. I think we're basically calling the initializer of the super class. I think this is what I meant. So if I'm right, please comment it down. If I'm wrong, then please correct me. Because see, even I don't know everything. I know some part, you know some part. So we both can learn from each other. Now we're going to define the layers here. Here we'll define the encoder layer. So the naming would be like different. So we say E1 representing encoder 1. Encoder block. Now here we need to give number of input and output. So let's say we are building a 2D segmentation. Okay. For a binary class. I think binary means 1. And the input would be RGB. So for RGB we have 3 channels. Okay. Number of output channel would be 64. Then E2. Same encoder block. Now number of input would be 64 and number of output 1. Now you would imagine why 64. Okay, so let's do one thing. Let's call this forward function self and the input x. Now we're going to call this E1 layers. So it would return skip connection S1 and P1. So we're going to call E1. We're going to give input x. Now this P1 would be output input for this E2. Now if you go to this block and see, so here input is 3, output is 64. So 64, 64, 64. If you see also here, the pooling does not need any number of channel. No channel changes are there. Number of channel would remain the same on pool. It is 64 only. But for your confirmation, what I'll do, I'll print the shape. Okay. Okay, so let's execute this. So if anyone out of you guys knows what this line is called, please comment it down. This is one of the interesting. Okay. So this is the input feature map or input tensor, not the feature map for now. So if you see, I've created tensor. Here it refers to number of patch, number of channel, then height and width of the image. So this is a random tensor. Model is equal to attention unit. So model is the object of attention unit class. Now we're going to take this model object, give it the input, and we'll run this program. See if there's any error or any problem is there. We're going to, okay. So you see, first is the skip connection. It has 64 channel, but height and width are same as input image. But this output of pooling layer also has same number of channel, but the height and width are decreased by a factor of 2, that is 128 by 120. So this would be input for our E2. Here you can see input, output number of channel of this pooling feature map is 64. So that is why we give 64 here and 128, that is output of that layer. So let's say S2 P2 self dot E2. Now input would be P1. Now let's repeat the same thing. Let's print S2 and P2. I hope you guys are enjoying this implementation. I hope it's really simple and understandable. So here we have again the skip connection where number of channel 128, height and width also 128 by 120. So don't confuse here. So first is the batch size, then number of channel, then height of the feature map, width of the feature map. Same here. Number of channel is 128, height and width is 64. Now let's implement the third encoder. Input 128 and output 256. Now I hope you will get why 128 here. How? I know you are smart guys and you would easily understand this fact. Now encoder part is done. Now we need a convolution block in between. So we're gonna call it the bridge part. We say B1. Con block 256 became 512. Then we're gonna call B1 here. We can say self dot B1 and input would be P3. Now we have B1. Let's print the shape of B1. Okay, so we have reached the output of B1. That is bridge part till bridge we are done. Now we'll learn about the attention. Okay, so this is the proposed novelty in this attention unit paper. So attention gate is a component that allows the network to focus on important regions of the input image while ignoring the irrelevant or noisy regions. So you can see it's a simple attention gate which just make sure that the important features are there and unnecessary features are removed. So how this is done, we're going to learn that via this block diagram. So first is it takes an input, then it takes the gating signal. Okay, so I've read the paper and this is the appropriate description because they usually use the term gating signal most. So I try to so if so this both the input and the gating signal, just treat them as two different inputs. This gating signal is I think skip connection. Okay, maybe I'm wrong with the naming here. Okay, so I'm sorry for that, but just see them as two different input. This is the input from the previous, this is basically the previous input, and this is a skip connection. So both of them passes via this conv layer and the base normal. Done, really simple. Then we add them followed by a ReLU activation function. So here what we are doing, we are basically make sure both the features, we have some layer where we learn something from both the input, then add them followed by a non-linearity. Then after that, on the combined feature map, we applied a convolution operation followed by a sigmoid. So sigmoid is really interesting. If you have observed any convolution network based attention mechanism, they mostly use sigmoid. Now you may be asking why is sigmoid? Okay, the simple reason is that if you talk in the mathematical term, if you give any value to sigmoid function, it would give you an output value in the range of 0 and 1. Now 0 and 1, the value between 0 and 1 act as the attention here. Okay, so just imagine it as a single value, let's say 0.1. Okay, so if you let's say multiply 10 by 0.1, it became 1. So value decreases from 10 to 1. So this is how it decreases the irrelevant features. Now let's say you have the output of sigmoid is let's say 1. Okay, or let's say 0.9. If you multiply 10 with 1, it became 10. Multiplied by 0.9, it became 0.9. It became 9. Sorry, it became 9. You can see when the features are really important, they do not get decreased, they remain the same, or they get really slight decrease in themselves. So this is how they manages to decrease the irrelevant feature and remain, and the necessary feature remains there. So now till now we are talking about single value. Now these values are generated for the entire feature map spatially. Spatially means that the attention map would have height and width and number of channel would be equal to 1. Then we got this attention map as the output of sigmoid. Then we multiply it with the skip connection or gating signal. The second input we multiply it with. and we get the output. So that is why initially what I've said to you, that this is a skip connection. It basically improves this skip connection by suppressing the irrelevant features. Okay, now let's try to implement this attention gate, and I think this is really simple. It's not that complex. So let's go to our text editor. Let's create another class called attention. So let me directly copy paste something here, because these things are repeating. So again, we need input and out. So here, if you see, we have two input. So here the input would be a list. Okay, what I usually use if input is a single value like here, so this inc would also be single. If let's say we have two input here, let's say x and y, like this, and this would be a list containing the input size, input number of channel of both the variable. So now assume this is a list and this is a single integer value. Okay, and then we're going to move forward. Now wg. Okay, so this is going to be sequential in nature. We have two layers inside it. First the convolution layer, and second the batch normalization. nn.conv 2d inc input 0. What I've told, this is a list of two values. Out c, kernel size is 1 and padding equals to 0. Okay, I forgot a comma. Then batch normalization will be out. So we are done with wg. Now we're going to say ws. Okay, so see, I've made a mistake. I think this wg here refer to gating and s refer to skip. So I hope you understand it, like don't get confused. This previous input from the previous block is the gating, and s refers to skip connection. So I think in slide I made a slight mistake. I hope you can adjust that thing. Okay, so we're gonna repeat same thing here, just a difference in the number of input. So this would be inc1. Okay, so now we're gonna move with the forward. This time we have two features, g and s. Just from the slide, okay, understand the concept. Just don't focus on the names. Names can be anything. Name does not much here. So first wg equals to self dot wg g, then ws self dot ws and okay. So now we have our output, so we need to add them, and after adding this followed by the relu activation function. Let me just write relu here. So I'll implement this, just don't worry thinking that where this thing come from. I'll implement it. So what will say self dot relu nn dot relu. Okay, again mistake, in place equals to true. So we are done with relu. Now after that we'll define another convolution layer with sigmoid as the activation function. So we add them here, we do not concatenate them. So the number of output feature of this output would be out only. Now we're going to say out self dot output, and input for this layer would be out. Now we're going to give some values back, that would be out into s. S refers to skip connection. So attention gate is done. Really simple. Now let's move forward with the decoder block. So decoder block is also simple. It's a combination of upsampling, attention gate, and convolution. So the decoder block is a component that takes the feature maps produced by the encoder block to generate the segmentation. So the ultimate goal of the decoder network or the groups of decoder block is to learn the semantic features and then finally predict the segmentation mask. So here we have two inputs. First is the input, that is input from previous. Let's say, see, if I write input, this means output of the previous block. So output of previous block act as input for the next. So input, then skip connection. So you know skip connection. Let's go back to the diagram. The skip connection, and from the origin block these arrows. So let's go to the decoder block. So first our input is upsampled by factor of 2. Then it goes into the attention block with skip connection. Then we have this output of attention gate, which we concatenate again with the upsampled feature map. After that it is followed by this convolution block and we get the output. Now let's implement it. So what we need to implement is decoder block. Okay, so this is the decoder block. We have INC again as a list because we have two input, then out as an integer. So first of all we need upsampling layer. So here we apply a bilinear interpolation. So we upsample using bilinear interpolation. Here we have written scale factor 2. This means upsample it by factor of 2. To factor of 2 means 64 by 64 feature would become 128 by 128. Okay, let's now move on to the forward function. X refers to output of previous block and S refers to skip connection. Self dot up X, we upsample it. Next we need attention gate. So we say AG attention gate, and it requires to input INC and out. Okay, so now let's understand a bit of things here. So see, this where's the diagram? This attention is getting first this upsample feature map. So when we apply upsampling, we just increase the height and width of the feature map, not the number of channel. So the input number of input channel would remain the same. Second is skip connection. So we simply take this list and put it here. And what is the output number of channel we want from this attention gate is out underscore C. So we say S equals to self dot AG. Then first input would be X, that is the upsampled feature map, and second is a skip connection. So we get an improved skip connection. Next we concatenate them. We concatenate followed by convolution block. So like in TensorFlow, we have a separate layer for concatenation. Here we use simple torch operation. In TensorFlow, you can also, I think, use tf dot concat. I think there's a function that x is 1. So x is 1 basically means we want to concatenate them on channel basis. So if you see, let's say these two things. So this is the channel axis, the 1. Okay. So we want to concatenate both of them on channel axis. So during concatenation, make sure your height and width are same, then only they are going to concatenate. This axis, one axis can be different. Now let's define our convolution block. Now just we need to give input. Okay, see? So we have concatenated both the features. So first is this X. What is this X? Upsampled feature map. It is same as X, so this would be INC 0. I hope you get it how this is INC 0. It's a list. See, this is the input, this is input 1, input 2. Here also in the list we have two values. On the first place would be number of input channel of X, on the second place number of input channel of skip connection. So here we have X, that is upsampled feature map, so we write X here, that is number of channel of first input. Then S is this, S is not this one S, okay, this is overridden here, so we take this S here, so we concatenate. So here the number of output channel is out underscore C, so we're going to copy it and add it here. And we also want the output channel of con block as out C, so we say X equals to self dot C1 X, and we're going to give this output of con block as the output of decoder. So our decoder part is done. Now let's implement the decoder block. So we're going to say D1. Okay, not here, we need to define the layers first. Decoder block, so B1 as the previous block output. Skip connection will be, okay, sorry, see, making a mistake, huge mistake. Here I need to define the number of channels. Okay, so let me just do some. Yeah, first with B1, then skip connection as third. Actually, I need to do this part first so that you can understand how we are working here. Okay, so these are the two input, and we need to write their number of channels here. So first is B1. You see, this is B1. Its output number of channel is 512. So we write 512. Next we have S third. S third is E third. E third number of output channel of E third is 256. So we write 256. Or what you can do, you can manually print the shape of B1 and S third. Let's do that here. And I hope my predictions are like right. 512 by 256, the number of channels. Let me run them again. Okay, oh yeah, this is mistake. Because this without this it would be incomplete. You can see 512 then 256. See, 512 256. This is how it is done. So we're gonna say D1. Now like this we're gonna have D2 and D third. And let's add these layers in the forward function also. Okay, so this is the decoder block. We have done with this. We are done with this part. Now we need the output layer, which is going to predict the mask. On 2D, number of input channel is 64. That from here, output channel is 1, kernel size is 1, padding is 0. And now we say output. Self dot output. Input would be D third, and we're going to give this back. Where it does not have any class like model where you put input and output and it builds the model. So this is simple. So we are done with attention unit. So we're going to get the output here, output. So let's say for this active input, what do we get? What shape do we have? Basically, when you implement any architecture, shapes are really important. So shapes tell you how we are moving forward. You can see 8 number of patches 1 because we have one class, and height and width same as the original input. Get it? So this is like the implementation of the attention unit. I hope like you enjoyed this video and you understand the attention unit. And if you still have any question, you can email me or you can comment it down. And do follow me on Facebook, Twitter, LinkedIn, etc. And don't forget to like, share and subscribe the video. Thank you. Have a nice day.